Honors physics or AP?
AP.
Wouldn't honors physics just be a better version of core stuff?
Harder version. All right. To pick up from yesterday, quick review. If you're looking for change in momentum, you can either go the mass times change in velocity route or the force times time route. Okay. One of those two is going to be definitive. That's what you're looking for. The other one's going to be a little fuzzy. Don't choose that. All right. Give that one a shot.
You said it's the one that represents What would you recommend? Yeah, that's pretty good. I should find my right and
Thumbs up when you have a guess. Have a conversation.
no idea.
No, yeah. Is that?
Oh, he said this one.
I think it fits, so it's a bigger change.
It's
I should really know what when is it starting? The smallest thing.
What do you say? Which one wins the race? Which one crosses the finish line first? B. Everybody good with that? This has a running head start. Okay. So, which one was on the racetrack for a longer period of time? A was. They experienced the same force, but A experienced the force for a greater amount of time. Therefore, it's going to experience a greater change in momentum. Now, B is going to have a greater amount of momentum at the end of the race. But I'm not asking for which one has a greater amount of momentum. I'm asking for which one experienced a greater change in momentum. Good with that? Next question. Thumbs up when you have a guess. Talk to your neighbor. Correct answer is got some C's, got an A, got an A, 2 A's, got a lot of abstentions. Which one wins the race? B wins the race. Why? Has less mass, has a greater acceleration. Which one experiences the force for a longer period of time? A. Okay. Here's the thing. Momentum is not solely determined by velocity. It's the product of mass and velocity. This is fuzzy. But this, in this scenario, is definitive. Experience the same force. A experiences that force for a greater amount of time. Therefore, it has a greater change of momentum. Good with that? It will be going slower. Okay. Now, but the mass compensates for that. Okay. In sports, you're told if you're dealing with a ball, regardless of what sport it is, you're coached, you're instructed, you're told to follow through. Good with that? So I want to know why. So here's a quick demonstration. What I'm going to do is I'm going to kick a soccer ball without following through and then with following through. Okay. What that means is I'm going to stop my foot the moment it touches the ball. Okay. And the way I'm going to do that is I'm essentially just going to kick the floor where the ball is. Does that make sense? Okay. So here's what a no follow through looks like. Okay. Following through, I'm not going to kick it any harder. I'm just going to let my foot follow through. Okay. How'd you like that? That was like up front in your face. Why did the ball go faster when I followed through? Yes, I carried with it. How could I put that with terms? Not more force, more time. Okay. I was in contact with the ball for a greater amount of time, therefore it gave it a greater change of momentum. Now, you might be saying, well, was it really that much more time? I mean, if you're trying to time it with a stopwatch, no, it was not that much more. Like, you're like, ugh. But if we took it and videotaped it in slow motion, at that scale, it is substantial. Okay, I recognize that this is like an archaic footage of this. But so soccer ball barefoot. If they didn't follow through, they'd stop right there. But they're going for another like 200ths of a second with following through. So no follow through, stop there. Okay. Now, this is more recent footage of a tennis ball being hit by a tennis racket. So you guys grew up with slow motion guys, is that right? That's your childhood? No, like, man. You've seen YouTubes of slow motion cameras, like footage? Yes, no, like that's a thing. Okay. Okay. Now, this is cool because it goes frame by frame. So here, if there was no follow through, we'd stop here. But notice how much more time goes on when the ball is in contact with the racket while the racket exerts a force. The ball leaves the racket, I think, there. Okay. And just that much more time makes a significant difference. Probably twice as much, maybe 3 times as much time. Okay. So let's just watch it again just for like appreciation's sake of slow motion things. Notice the jello effect that the ball goes through. You see that? That's so cool. It was like the inertia of the ball is like I want to stay at rest. And then is like pancaked. I mean, that is just so cool. And then this is cool. This is like a divot, like that is like being concaved, and then it's like super cool. Watch some slow motion videos when you go home tonight. You're like, it's cool. All right. I recognize this is random, like how many times you ever drive into a haystack. Like the only movie I've ever seen this is like Back to the Future, and that's my childhood, so I don't even expect you to know that reference. But just pretend. Tell your neighbor what you think.
What do you think, Jason?
Correct answer is C. How'd you figure that out? You go from this way or this way. Mass times change in velocity or force times time? Mass times change in velocity. That's definitive. They had the same mass. They both started at 60 and both went to 0. Both experienced the same change in momentum. Okay. So here is a truck hitting a brick wall. Okay. Here's a truck hitting a haystack. Okay, have you guys ever seen those yellow, like the trash can barrel looking things? They put them in front of the center column of an overpass on the interstate, or like if the interstate's going to divide and they like there's a median thing, they'll stick some of these sometimes inside of guardrails. So they're filled with sand or water, depending on what county it is. Okay, but just so we see this again, brick wall. Good with that. Okay, a follow-up question. Everybody good with brick wall? Changes momentum in a small amount of time. Next question, same scenario. Correct answer is A. Okay. I mean, obviously, look at the results of the trucks. Okay. So both experience the same change in momentum. The brick wall just did it in a small amount of time, which required a big force. The haystack did it in a longer period of time, therefore requiring a smaller force. You all right with that? Okay. If I take time and I bring it over here, I have net force is equal to delta P over delta T. You remember this equation? This is the rate at which position changes, which is velocity. This is the rate at which momentum changes, which is equal to the net force. This is actually how Isaac Newton wrote his second law. It wasn't F equals ma. It was force, the net force is equal to the rate at which momentum changes. Okay? So if you have to change your momentum quickly, that requires a large force. If you're changing your momentum over a longer period of time, not so quickly, it doesn't require a big force. Does that make sense? Where that's coming from? Last question's on this haystack brick wall. Talk to your neighbor. Correct answer is C. They both experience the same change in momentum, therefore they experience the same impulse. Good. Have a conversation. What do you say? I agree that the impulse is 0.8, but what are you missing? Time. Correct answer is cannot be determined. You've no idea how quickly that momentum changed. You won't be able to know the force. You need to know how quickly and how much time the momentum had to change. That makes sense? Last question. Talk to your neighbor. Correct answer is I heard 1B and 1A. Got a B, second B, and a lot of abstentions. So the rate of momentum change which one is experiencing a greater force? Mack truck is experiencing twice as much force for the same amount of time. Therefore, it's going to have a greater change of momentum. So it's going to change its momentum more quickly. Quick answer is A. Okay. The motorcycle speeds up faster, absolutely. But momentum is not solely determined by velocity. Okay. Good with that? All right.